Hello everyone. In this video series, I will cover the entire current electricity unit coming under GCE Advanced Level Physics. So here I would like to mention some of the topics that we will see in the course of time that are electric current and Ohm's law, system of resistors, electric cell and electromotive force, energy dissipation due to flow of charges, simple closed circuits and Kirchhoff's laws, meter bridge and potentiometer, electromagnetic induction, etc. And in this video, I will cover electric current, drift velocity and electric resistance. Okay, so first let's see what is electric current and what makes a flow of current inside a conductor. And before talking about the current, I would like to discuss the behavior of electrons in a metal conductor in absence of an external electric field. No electric field means no potential difference is applied to the conductor. In this case, we know that the electrons in the metal are freely move in random high speeds in random directions. So if we consider the average velocity of these electrons through a given cross-sectional area, then we will see that the value is nearly zero because there is no overall motion of these electrons. But when we apply a potential difference across the conductor, then there will be an electric field produced inside the conductor in a direction from positive to negative side of the applied potential. In the previous unit, I mean in electrostatic field unit, you may have studied that the charged particles in an electric field experience a force. And since electrons are negatively charged, they will experience a force in a direction opposite to the electric field, and that is given by the following equation. Now, due to this electric force, all the electrons will move, or I can say accelerate towards the positive side of the conductor, which causes an electric current. And we take current is in the direction of flow of positive charges, which is to say current flows in a direction opposite to the direction of electrons move. Well, now I can state what is current is. It is the rate at which charges flow through a cross-sectional area of a conductor. That is, the number of charges passing through a given area in 1 second of time. And now let's consider a q charge passes through a given cross-section of the conductor in time t. Therefore, I can say that the flow of charges in 1 second is q divided by t. So the current I equals q divided by t. Therefore, I can rearrange this equation and write q equals it. And current is a scalar quantity and the SI unit for current is ampere. And now we will see the definition of ampere. It is defined as the current flowing in each of two long, straight and parallel wires exactly 1 meter apart, so that there is a force of exactly 2 into 10 to the power minus 7 Newton per meter of length acting on wires. Well, now let's see the relation between total charge and the number of electrons of a conductor. And the relation is simply given by the equation Q equals Ne, where Q is the total charge, N is the number of electrons and E is the charge of an electron. And we know that the charge of an electron is minus 1.6 times 10 to the power minus 19 coulombs. Next, we will see the current density. It is the amount of charge that flows per unit time through a unit area. So current density is equal to current over area, that is J equals I over A. And the current density is a vector quantity. And let's consider two locations of current carrying conductor having cross-sectional areas A1 and A2 and the current densities J1 and J2 respectively. Since we know the same current flows through the conductor, I can write following equations that are I equals J1 times A1 and again I equals J2 times A2. And from these two equations I can rewrite J1 times A1 equals to J2 times A2. Okay, now let's move to drift velocity. We have learned that the electrons will move in opposite direction to the electric field when we apply the potential difference to the conductor. And these electrons travels within different velocities, and if we calculate the mean value of these velocities, we will get the drift velocity. Okay, now let's derive an expression for the drift velocity. For this, let's consider a conductor having n number of free electrons per unit volume, or we can say n is the free electron density of the conductor. Therefore, the total number of electrons in the volume of A times D, as you can see here in this image, is n times AD. So, to get the total charge in that volume, we can simply multiply with the electron charge, then we will get Q equals NEAD, right? And we said that these electrons move with mean drift velocity. Therefore, we can get the time that an electron takes to travel simple d distance by simply dividing the distance by the drift velocity, as you can see the equation in the third row. Now we know that the current is charge divided by time, so we can use above two equations and it will yield I equals NEAVD. So this is the equation that we have for drift velocity. And I would like to recall the physical quantities involved in this expression. So N is the free electron density of the conductor, E is the charge of electron, and capital A is the cross-sectional area of the conductor. Well, and here I would like to discuss a little further about drift velocity, which is not in syllabus, but I hope it will help you to understand drift velocity clearly. In fact, I believe this video is not complete if I didn't talk about that. So, as we know, when we apply the potential difference to a conductor, the electrons in the conductor experience a force and they will move opposite direction to the electric field. And this force is given by the equation F equals minus E times capital E, where capital E is the electric field intensity. And here minus is because electron is negatively charged, and also it tells us that the force acting on the electrons is opposite to the electric field. And for the simplicity of explanation, I'll consider only one electron in the conductor, and now we can use Newton's second law to this electron. So I can write F equals ma, where m is the mass of the electron. And we know what is the force acting on the electron, therefore I can write minus E times capital E equals ma. So if we subject acceleration in this equation, we will get A equals minus E times capital E divided by m. And we can see that the acceleration of the electron is directly proportional to the electric field, or we can say directly proportional to the potential difference. Okay, now we know the acceleration of this electron. So if we use V equals U plus AT, assuming that the electron at rest at t equals 0, we get velocity is equals to acceleration times the time. And if we substitute the acceleration, we will get V equals minus E times capital E times time divided by mass. Here also minus sign means that the velocity of the electron is opposite direction to the electric field. If we consider only the magnitude, we can write the following equation. Now let's consider how the velocity of an electron inside the metal conductor varies with time when we apply the potential difference. So we have the velocity versus time graph of an electron, assuming that the potential difference is applied at t equals 0 and electron starts to move at rest. As soon as the potential is applied, electron will accelerate with constant acceleration, and in very small time it will collide with an atom in the conductor and velocity drops down. And again it will accelerate and collides with another atom, and again velocity of the electron drops down. Similarly, electron will move throughout the conductor. So if we take the average value of these velocities, we will get the drift velocity. Okay, now we will do one example from drift velocity. A certain copper wire with a cross-sectional area of 3 mm squared carries an electric current of 2 amperes. Density of copper is 8.9 times 10 to the power 3 kg per meter cube, and the atomic mass of copper is 63.5 gram per mole. Each copper atom gives one free electron. What is the drift velocity of electrons inside this copper wire? Here I would say you guys to pause the video and try this problem at least once before we look at the solution. So here we go. We know the formula which gives us the drift velocity, that is I equals NEAVD. Here I is the current and it is given in the question, and A is the cross-sectional area which is 3 millimeter squared, and E is the charge of the electron which is a fundamental constant of nature, so we know that too. Therefore the only missing variable is N, which is the free electron density of this copper wire. So our first task is to find N, that is the number of electrons present in 1 cubic meter. Since each copper atom contribute only one electron, the number of free electrons in 1 cubic meter is the same as the number of copper atoms in 1 cubic meter. Therefore, all we need now is to find the number of copper atoms present in 1 cubic meter. So we can calculate that very simply. Just divide the density of copper by the atomic mass of copper and multiply it by Avogadro constant. Here the density is in kilogram and atomic mass in grams, so you need to change either one of the units to into the same as the other one. And if you calculate this, then you will get the free electron density is equals to 8.4 times 10 to power 28 per meter cube. Now we can find the drift velocity. So let us substitute all the values in the above equation and let's do the max. We will get the drift velocity of electrons is equals to 0.5 times 10 to power minus 4 meters per second. So as we can see, the drift velocity is a very small value. And here I recommend you to do electricity essay question from 2000 A-level paper. Next, we have to say a few words about the potential difference. It is the work done by the electric force when moving a +1 coulomb charge from one point to another point inside the conductor. Next, electric resistance. When an electric current flows through a conductor, the conductor offers some obstruction to the current, and this obstruction is known as electrical resistance. This obstruction is mainly caused by the atoms and positive ions of the conductor. Now let's consider a piece of conductor whose length is simple L and cross-sectional area is capital A. And I can say that the resistance of this conductor is directly proportional to its length. For example, imagine a situation where you run a race of 100 meters as well as 400 meters. You may finish the 100 meter easily, but you will obviously feel more difficult to finish 400 meter. Similarly, when the length of the conductor is large, it will have large resistance. And the next thing I can say about the resistance of the conductor is it is inversely proportional to the cross-sectional area, which is obvious, right? For example, again imagine a situation where you and 10 of your friends running a 100-meter race in a track of 10 meters width. Now what if the width of the racetrack is reduced down to 2 meters? You guys will experience more obstacle to run, right? And that's the same thing happens to those electrons when the cross-sectional area of the conductor is smaller. So from the above two relations, I can write resistance is proportional to length over area. And finally, we have R equals rho L over A, where rho is the resistivity of the conductor. And it is a characteristic property of the material. Now let's see the definition of resistivity. It is defined as the electrical resistance per unit length and per unit of cross-sectional area at a specific temperature. And unit is ohm meter. And our next topic is electric conductance. Conductance is the reciprocal of resistance. So conductance equals 1 over resistance. Therefore, S equals 1 over R. Units per ohm or Siemens. Finally, we will see what is electric conductivity. Electric conductivity is 1 over resistivity. So sigma equals 1 over rho. Unit equals per ohm per meter or Siemens per meter. Okay, so that's all for this video, and I hope I can meet you all once again very soon with Ohm's law. Until then, take care.